Good morning, class. Today we're going to talk about Chapter 5, Diffusion. So to start off the class, we're going to do a demonstration. So the materials we have here are two beakers, one filled with ice water, and the other filled with boiling water. So what we're going to do is put one drop of food coloring into each beaker, and we're going to look at what happens. So while we're doing this experiment, look at what is happening to the food coloring and what the difference is between the cold water and the hot water. So can anybody tell me what's happening to the food coloring? Yep.
It's diffusing.
Right. And what is the difference between the hot water and the cold water? Yep.
The hot water is diffusing faster.
Exactly. So in the hot water, the molecules have more energy, so they're moving faster, which means it's diffusing more quickly. Oh. So these are the main objectives that you should be able to complete by the end of today's class. They'll be really important for the exam, so at the end of class, make sure you understand all of these concepts. So we're going to give a brief outline of what we're going to do today in class. First, we're going to do an introduction to diffusion, then move on to diffusion in solids, the different mechanisms by which diffusion occurs, what steady-state diffusion is with an example, and the factors that influence diffusion. Then we'll sum everything up and take a look at what the homework problems are. So, the first question we have is, what is diffusion? Can anybody give me a definition for diffusion?
Material transport by atomic motion.
Right, so that is exactly the textbook definition. You also probably have heard that it's the motion of atoms from areas of high concentration to low concentration. So can anybody tell me some examples that they can think of where you see diffusion in everyday life? Yep.
Balloons.
Balloons. Why in balloons?
When they start deflating over time, even though they're still sealed.
Right. Anybody else?
When you're cooking, you can smell it in the house.
Right, exactly. So some other examples are air freshener or an oxygen sensor, where the whole point of the sensor is for the oxygen to diffuse through a membrane so that it gives you an output of the amount of oxygen in the air. So what do all of these examples that we just talked about that we see every day have in common? Anybody know?
We see a lot of gas diffusion.
Right. So the examples that we're seeing here is a lot of gas and liquid diffusion. But in this class today for material science, we're going to focus on diffusion in the solid. So the easiest way to think about diffusion of solids is an example of a diffusion couple. So you take two pieces of metal, in this case it's copper and nickel, and you put them together so that there's intimate contact between the surfaces. And at room temperature, all of the atoms are completely separated. The copper atoms on one side and the nickel atoms on the other side. Then in the experiment, you heat the metal blocks up to a really high temperature, but just below the melting point, and then you bring it back down to room temperature. So what you see in the block when you do some chemical analysis is that on the very outsides of the block, you still see 100% copper and 100% nickel atoms, but in the middle, the atoms have migrated, so now they're mixed. So the next thing that it's important to note is the difference between interdiffusion and self-diffusion. So in interdiffusion, there are two different metals where the different metal atoms are diffusing with each other and switching and migrating places. In self-diffusion, it's just with one pure metal, and the same atoms are interchanging with each other. So there are two different mechanisms by which diffusion happens. vacancy diffusion and interstitial diffusion. The first one, vacancy diffusion, is when the atoms interchange from their normal place in the lattice to an adjacent vacancy, which we talked about in the last class. This mechanism can happen both with self-diffusion and interdiffusion. Interstitial diffusion is when the atoms migrate from one interstitial site to another site, so the sites that are in between the normal lattice. So these interdiffusion particles are normally the impurities that you see inside the metals like hydrogen and carbon and nitrogen, because they're very small and they fit in between the normal lattice. Interstitial diffusion is much faster than vacancy diffusion because these atoms are so much smaller, and there are many more interstitial sites in a lattice than there are vacancies. So next we'll talk about what it means for diffusion to be at steady state. So normally diffusion is looked at as a function of time, and in order to look at what the rate of the diffusion is, we look at the diffusion flux, which is J, seen in equation 5.1a. And we also have the differential form of this equation. So can anybody tell me what it means for diffusion to be at steady state? Yep.
Input in equals input out.
Right. So another definition of it being at steady state is when the diffusion flux is constant as time goes by. So one example to look at the steady state diffusion in an experimental setting is to have a piece of metal, and then you're diffusing gas through the metal. And then in graph B, you take measurements of the concentration through the metal as a function of the position in the metal, and you get this graph. And the slope of that line is known as the concentration gradient, which will be important for the next section. So from all of this information, we get to Fick's first law. So you're looking at the concentration gradient, which is proportional to the flux. So can anybody tell me why there's a negative sign in this equation? Yep.
It's flowing down the concentration gradient.
Exactly. The negative sign accounts for the fact that the diffusion is flowing from high concentration to low concentration. So now we're going to do an example problem. I have a handout here for you to work on. So at first glance, this looks like a huge chunk of text. So we're going to break it down into a 4-step process to solve the problem. So first, you look at the problem statement and circle or highlight all of the different variables that you see that could be useful for the problem. Then write out all of those variables and their units, and then you have to take into account which information might be extra. So are there any variables that the problem gave you that you don't actually need? Then you write out the necessary equation, and then plug in all of your variables and solve to get the answer. So I'll give you a minute to solve that.
Can you go back a slide to the flux equation?
Yep. All right, is everybody all set? All right, so somebody tell me what they got for an answer.
1.5 times 10 to the negative 9.
And what are the units for that?
Kilograms per meter squared times second.
Exactly. So we'll quickly go through this for anybody who didn't get the answer. So I highlighted all of the important information in the problem that you need to pull out. So as you can see, the temperature is extra information. You don't need that to solve the problem. So it's there kind of just to trick you and to make you think about what variables you actually need. Plug everything into the equation, and you get exactly that answer. So the next thing we're going to talk about is what factors influence diffusion. So the first thing that we look at is the different types of atoms that are diffusing. So the different types of metals diffuse at different rates, giving you different diffusion coefficients, which you can see in this table. And the second thing that greatly influences the diffusion is temperature. So we saw at the beginning of class with the hot water and the cold water, at higher temperatures, diffusion is faster. You can also see in this table between the difference between the 500 and the 900 degrees Celsius that the diffusion at 900 degrees is a lot faster. So there's an equation that we look at to determine how temperature affects the diffusion coefficient. So the different variables that we're looking at are the diffusion coefficient, a temperature-independent constant, D0, the activation energy for diffusion, which is Q, the universal gas constant, R, and the temperature in Kelvin rather than in Celsius. So now you can flip your sheets over to the second example and do the same four-step approach where you look at the problem, find all of the information that you could possibly need, write out your variables with the units, then the equation, and then you can solve. Yep?
Can you go back to the last equation?
Mm-hmm. Does everybody get an answer? All right, so we'll quickly go over that. So using the same approach, the important information is highlighted. In this case, you just need to pick the appropriate values from the table. So you're looking at magnesium and aluminum, so you just need to find the correct row. And then you use the equation we just talked about, plug everything in, and you get your answer. So something that's very important to pay attention to are your units. So in this case, the activation energy is given in kilojoules, but in the equation, it needs to be in joules. So you need to make sure that you're converting your units and making sure that everything cancels. So to wrap up today, I want everybody, when they go home, to think about these questions. So the first is diffusion happening faster in a liquid or a gas, and why would that be the case? And then, where does solid diffusion rank compared to liquid and gas diffusion? So, summing up everything we did today, we talked about what diffusion is, just on a basic level, what the different mechanisms are that diffusion happens by, so vacancy diffusion or interstitial diffusion, what it means for diffusion to be at steady state, and what are the different factors that influence diffusion. These are some important terms to know. These will be necessary for doing well on the exam, so make sure that you can define all of these terms. This is just a summary of all the equations that we learned today. They're super important, so make sure you can write out the equation and define what all of the variables are in each equation with their given units. So the homework problems that will be due next week are given in red, and on the bottom there's some additional problems that you can use for studying for the exam. So in the next class, we'll talk about non-steady state diffusion and Fick's second law and how that relates to diffusion in solids.